Folks, in this video, we are going to continue looking at Gauss's law and how we apply it. And this is kind of a deeper dive into the individual steps that are involved in Gauss's law, just to make sure we understand them. So if you have some charged object, remember for Gauss's law, we're looking at things that are sort of highly symmetric, things that are infinitely long, or a point charge, or a sphere, or that kind of thing. And we want to find the electric field from a point P, 1 meter from an infinite charge cylinder. This could be a wire or a cylinder. It depends on what you're looking at. Technically, all wires are cylinders and are not actually one-dimensional, although they can be approximated that way. And that's really what we're doing here, right? We're saying it has a linear charge density. We're interested in how much charge it has per meter. So we're not going to worry about how wide this actual object is. So we visualize and sketch the field. That's the important thing. For objects like this, it can be helpful to draw it from two perspectives, right? The end view and the side view really give you a full picture of the fact that there's no electric field going left or right here, only radially outward, so up and down and in and out of the page and all of that. And so we want something that is the same along the same distance from the charged object, but we need to make sure that that shape goes around and stays the same distance from the charged wire. And so here's a three-dimensional picture, but of course this is much harder to draw for us. This is someone made in a computer, but the shape we need, right, is something that is either parallel or perpendicular to the area the electric field is. And most often what you'll find is it's actually both. Some part of it is parallel and some part is perpendicular. So in this case, the cylinder is probably our favorite shape to use for these because it is so simple. It only has three sides, but they are oriented differently compared to these objects. We even use it when we're dealing with that infinite plane, which in some ways, when you're drawing it, it might make more sense. You might think it makes more sense to make a cube, and you certainly can. There's some examples of that in our practice problems. The electric field is parallel to the end caps, which means it is perpendicular to the area vector, and it's perpendicular to the cylinder surface, which means it is parallel to the area vector, which is exactly what we want, right? So because it's cylindrically symmetric, and it's either parallel or perpendicular to the surface at all points, we can do useful things, right? We know that lambda multiplied by the length of that will tell us the Q enclosed, right? And we can use the Gaussian surface to answer the stuff on the left-hand side of the equation. So whenever we do these problems, there's really two pieces. There's the how much charge is enclosed part, which sometimes is fairly simple. Here, it's just going to be lambda times the length of the cylinder. Sometimes it's a little bit more complicated when there's a charge distribution and maybe the Gaussian cylinder or surface is inside of that object. So you just have to watch out a little bit about those things. And then there is the part about the Gaussian surface, the E dot dA. This is the part where the electric field information comes from. And it's also the part we need to make sure we understand that could, although it's a continuous surface integral, we're usually going to look at it piecewise. There are three different surfaces here, so we're going to kind of address them each individually. You address each end cap, or in this case, the end caps you can kind of address together, and then you talk about the lateral surface, right? So when we're looking at this, right, we know that the length of the cylinder is something L, whatever it is. So Q enclosed is lambda L. Then we look at the Gaussian surface side of the equation. We say, well, the electric field is the same everywhere along the lateral surface. And the area of that lateral surface, when you add up all the little bits, is 2 pi r L. The end caps, right, you need to justify whenever you're doing this that those should be zero. So the easiest way to do that, I think, is to just draw little area vectors and say, oh, look, they're perpendicular, no effect. Then we can go in and we can cancel out that L, which is good because it shouldn't matter how long the Gaussian cylinder is. It should only matter, Gaussian surface is how far away it is from the line, as we've learned. And we end up with this, lambda over 2 pi r epsilon naught. We can plug everything in, and we can get a numerical value. We've already done all the work to think about the electric field direction, so we don't need to do that. Sometimes the hardest part, and I sort of have alluded to this, but it's worth thinking about, is finding the Q enclosed, right? So if you have an insulating sphere, if it's a conducting sphere, if you go inside, the electric field's 0, there's no charge enclosed. That's easy. But if I give you something like this, and I say, well, this has a charge density that isn't even uniform, it's equal to kappa r squared, right? Some formula here where it becomes more dense the further out you get, and it's less dense in the middle. Whether that's realistic or not doesn't really matter that much here, but we can think about it. So if I want to enclose some charge, if I want to enclose the entire sphere, I need to add up all the charge that's inside. If I want to do a different Gaussian surface, maybe I'm interested in the electric field at some distance, little r, less than big R from the center. There still has to be an electric field. We know only at the very center would the full shell theorem take over. So we would like to be able to calculate what it is. So the way you do this is you think about Q enclosed as an integral, the sum, a continuous sum of all those little bits of charge. And this is very much like finding center of mass or moment of inertia, right? We have rho as a function of R multiplied by dV, the little bit of volume. But if we're talking about a spherical volume, well, then that's just 4 pi r squared, a spherical shell times a little bit of thickness, dr. And now we're in business, right? Because we have from 0 to r, the formula for what rho, or the charge density, is a function of r, multiplied by 4 pi r squared dr. And so we can go a little bit further in there. Everything in there is a constant except for r. And so you end up with r to the fourth dr, the integral of that from 0 to r. And you can actually solve for a number as long as you know what r is and you know what that kappa is, which would be given things that you can find inside of the sphere. Now, this also works for a cylinder, right? The formula is a little bit different, right? If you have a big thick wire and you're interested in the electric field inside of it, again, if it's an actual wire made of metal, all the charge will be on the outside and there's no effect once you're inside. But if it is an insulating rod of charge, maybe it's a piece of plastic or something like glass, which we often use for electrostatic examples, then the charge could be distributed throughout it. All right, so that is the end of that, and we are going to practice a few of these things when we come together on our next class block, which I can't remember when that is. That doesn't really matter. So I will see you all then. Good luck with this. Bring questions.